Hey everybody, welcome to this month session for our ACV meetup. Sorry for missing the last two, but it was a bit of some reasons which were internal and external that we didn't make it, but the most important part is we're here today. I'm very happy we have Mathieu today. He's a researcher from EPFL as well as ClearSpace, and I think he will introduce himself afterwards by himself. Just for you as a reminder, he will give a talk about how they use deep learning at ClearSpace. And if you have questions, you can ask during the talk or note your questions down, and then we have them afterwards. And we'll definitely have a Q&A session plus a little discussion at the end. You're all invited to stay for that. And then I would say, Mathieu, thanks for coming, and the stage is yours.
Thank you. So let me share my screen and bring up my slides. Let me know if you can not see my slides, but that should be fine, hopefully.
No, it's all clear. Yes.
Yeah. It is clear or it is not clear?
Yes. We can see it clearly.
Okay, good. So thank you very much for inviting me here. So I have sort of a dual position. Half-time, I'm a senior researcher at EPFL, working in the area of computer vision and machine learning. So anything that has to do with machine learning for image analysis, as you also do a lot in your company. And in particular nowadays, a lot of deep learning. And I am an artificial intelligence engineer at ClearSpace at halftime as well, working also on image-related problems. And so what I'm going to talk about today is mostly the research that we've done on the EPFL side, but with a clear motivation for application at ClearSpace. It doesn't mean that it's the technology that will actually fly this current mission, but definitely if it's not this time, it might be in the future. And so in particular, I'm going to talk about 6D object pose estimation, and here's the general idea of why I want to be able to do that. So nowadays, the space agencies estimate that there are more than 34,000 debris larger than 10 centimeters in diameter in the Earth's orbit. So this is a visualization of these debris, the tracks of these debris surrounding the Earth, essentially. Now, these debris can be non-operational satellites, which we know of, and they can be actual debris that are the results of a collision between two satellites, between non-operational satellites, between a non-operational satellite and an operational satellite that has happened in the past. Now, the number of such debris is rapidly growing. And the problem is, as there are more and more debris, then there's an increasing risk of collision between active and non-active satellites, which means that the number of debris will grow again. And we may end up reaching the point where we cannot really safely go to space or beyond the Earth's orbit or even in the Earth orbit in the relatively near future. So there are a few missions that are being developed. Examples of this are the one by ClearSpace, ClearSpace 1, but also one by Astroscale, that's called LZD. And the goal is to demonstrate the feasibility of non-cooperative debris capture. So the idea, as illustrated in this video, is, in particular case of ClearSpace, to build a chaser that will look like this, that has kind of arms, and that will go and grab a debris. And once it's grabbed this debris, it will go and release the debris in the atmosphere so that it burns. Now, to be able to do this, we need to be able to understand where the debris is relative to the chaser. So we need to understand, on one side, the 3D position of the debris relative to the chaser and the 3D orientation of the debris with respect to the chaser, so that we can grab it safely, approach it safely, and grab it safely. And so in general terms, this is known as the problem of 6D pose estimation. So the goal is, given an input image, to estimate the relative 3D translation and 3D rotation of the target, the debris in our case, with respect to the camera that acquired the picture. And so 6D because 3D translation and 3D rotation. And so here I'm just showing this on a synthetic image of the Vespa, and we're seeing that on one side we can represent a bounding box of the debris, knowing its position. We can also show this small coordinate system to illustrate the fact that we're correctly estimating its 3D pole, its 6D poles, so 3D rotation and 3D translation. So let me tell you how we're doing this, but I'll start with saying a few words in a more general computer vision context and in the context of general object 6D pose estimation. So the way we're doing this is we're doing this by deep learning, and given the input image that here may represent even multiple objects, right? Not just a single debris, but multiple debris if you want, and would like to estimate the location of key points with the deep networks, and these key points are just illustrated here with stars. And once we've obtained the location of these key points, if we have a 3D model of the object of interest, and we know where these 3D key points, where these key points are in the 3D model, then we can estimate the rotation and translation using what's referred to as a perspective endpoint algorithm. So this is a traditional method. Essentially, you have correspondences between 3D points and 2D points. If you have enough such correspondences, then you can estimate the pose. So rather than directly trying to regress the pose with a deep network, we regress the position of key points, and we then estimate the pose from these key points. In particular, the key points that we use are the corners of the bounding box of the object. So you see that they're not necessarily exactly on the object simply because it's the 3D bounding box projected in the image. So in terms of architecture, we drew inspiration from object detection, this YOLO architecture. So fairly standard architecture in terms of operations, convolutional layers to get to a feature map. And then eventually, once you have some resolution of feature map, spatial resolution of feature map, then at each pixel, if you want, in this feature map, will make predictions. So YOLO does this for object detection. So at every cell, they will predict whether there's an anchor bounding box that is active or not, so that you can detect the object. And we'll do something similar, but rather to predict the location of key points. So in fact, because we're using this architecture, we're not predicting the location of each key point a single time, but multiple times. We make local predictions. So given the input image, you have a grid that represents essentially the feature map on the input image, and then at each location of the grid will predict the key point locations for the object that's under this grid. So if it's something that's under the background, of course, we will not predict any key point location, but for any grid cell that is on the object, we're predicting the location of the key points. Essentially, each local image region provides a vote for the key point locations. So it looks like something like this. For every small cell, we'll get the position, a prediction of the position of the 8 key points of interest. So that gives us an overall framework that is taking the image as input. This image passes through a few convolutional layers to extract features, and then we have two heads, one that essentially computes a segmentation of the object. So if we have multiple objects, at each voxel will also classify to which object that particular voxel belongs. And then at the same time, we're predicting for every local cell the position of the key point. So we'll see that for each object, we have 8 sets of key points that should be ideally representing the corners of the bounding box. And so the colors here indicate the different objects that you can see. Once we have this information, in particular these key points, we can do a ransack-based PNP to obtain the pose, and we'll see that the pose is correct by projecting the 3D model of the object back onto the image and just showing the contour of this 3D model on the image with the estimated pose, so showing that the contours matches the true contours quite well. Now, of course, we have lots of predictions. So I said that we do a ransack-based PNP algorithm, but in fact, we do something that's a little bit more advanced than this. With each candidate key points, we predict a confidence measure telling us whether we trust this key point or how much we trust this key point or how much we do not trust this key point. And then we'll select for every key point the 10 best candidates, the 10 candidates for which we are the most confident. And given these 10 candidates per key point, we'll use a ransack-based PNP algorithm to estimate the pose. So 10 key point selection for each set of key points, and then PNP to get the pose of the object. So the nice thing about the method is that we doing local predictions. So that means that we can focus on the regions where the object truly is and be more robust to, for example, occlusion. So here, I'm going to compare this to a global method. So before our work in that respect, the people were doing global predictions. So essentially detecting the object with a global bounding box, and then given this detection, predict the pose. And that can be a bit rough because, here there's this other object that's in front of the other one, so you don't see it very well, and so you're a bit less accurate. Whereas in our case, we are predicting at every location in the image the key points. We have more predictions where you can discard this region that does not belong to the object of interest and then get a more accurate reprojection of the model given the pose that we obtain. And so here are the results on a standard benchmark. So you see, we're doing here pose estimation independently in every frame. So there's no notion of temporal consistency. You see, nevertheless, that, well, of course, there's a little bit of a jitter, right? But it's still doing pretty good predictions in the frames of this video. We see we can handle a number of objects with some occlusions between the objects and viewpoint changes. So here, I believe this is the YCB video benchmark for 6D object pose estimation. So we were quite happy with this. We published this, and that was giving us good results. And then we thought, okay, let's now try to see how this works on space type of data for the kind of application that we're interested in. So estimating the pose of a satellite. And at the time where we did this, there was a competition that was opened by the European Space Agency and Stanford University on the task of satellite pose estimation with a synthetic data set. So we thought, okay, well, we'll compete in this competition with our method, and we'll see what happens. So there was some time to try this, and quickly we realized that there's a much bigger challenge when we're dealing with satellites. Now here in standard benchmark, you see the objects are roughly always at the same distance to the camera there, and all of these benchmarks are similar to this. Essentially, you see a bunch of objects on a table in front of you, and it's more meant for robotics grasping than it is meant for space application. In space, we'll see the satellite very far away, so you can have something that is at 20 meters from you. You still want to estimate its pose to understand how to approach it, but you also want to estimate the pose of the satellite when it's 2 meters away and you actually want to grab it, right? So we realized that we were not dealing very well with these changes of depth of the satellite, and because of the apparent size of the satellite varied much more than in the standard benchmarks. We developed an initial solution for that pose estimation challenge that allowed us to finish second in the challenge, so we're still quite happy about it. That was relying on 2 stages, essentially a first stage to detect where the object was, given a first detection of the object, then zoom in on the region of interest and refine the pose of the object. And that was what we were doing when the object was far away. That worked reasonably well, but it's not very elegant to have these 2-stage strategies. So we moved on to a more modern version of it by using this notion of feature pyramid. So what's a feature pyramid? They were introduced for object detection. And so they work as follows. You get an image, you extract features as usual, and then at each level of these features, you will further extract pyramid features that you will merge with the previous ones. And now you will not make a single prediction at the final level of the feature map, but you will make predictions at multiple levels. So essentially, these levels represent different scales of the object, different resolutions in your feature map. So you should be able to handle large objects at low resolution and small objects at higher resolution in your map. And then you do these predictions at the different places in your network, and then you can somehow merge these predictions. So we use this idea for 6D pose estimation and got a network that does essentially that. So encoder, decoder network. But now, instead of making just a prediction at the very end, we're making multiple predictions at different stages of this network. At each stage, we're doing the same key point prediction. So we have many key point predictions predicting for the different levels. And then we can merge all of these key points and use a ransack PNP to get the pose of the satellite. So similar idea to what we had before, but doing predictions at multiple stages to better handle the depth range that happens in satellite data. To test this, we also created data sets beyond the one from the Kelvin's challenge. And we did this in collaboration with the Realistic Graphics Lab at EPFL. This is the lab of Wenzel Jakob. They have renderers they design their own renderers to have realistic images. And they did one for space. In a particular case, we were interested in using a wide angle camera so that we could also see the satellite when it's very close to the chaser. We generated 30,000 images, distances between 1.5 meters and 30 meters. And we did this for two satellites. One is the Vespa that is shown over here, and the other one is the Swiss Cube that I showed on the previous slide here. In fact, the distance range that I'm giving you here, 1.5 meter to 30 meter, is for the Vespa. The Swiss Cube is much smaller. So the Vespa is about 2 meters in diameter. The Swiss Cube is 10 centimeter in diameter. So of course, the Swiss Cube at 30 meter, we cannot really see it with a wide angle camera. So it would simply not work. And so these are examples of the images. And we'll see that, in some cases, well, the satellite is very close, we can see it quite well, but in other situations, the satellite is far away, we see that there's something that's very hard even for us to see this. In some other situations, it's a bit closer, but because of the Earth brightness, it's hard to really see it very well either. So it's a fairly challenging data set, even though that's a synthetic data set. We tested our approach on this, and this is a curve showing the pose error, which we're measuring here as an average point-to-point distance between the model that is transformed with the ground truth pose and the model that is transformed with the predicted pose. And it's the point-to-point distance relative to the model diameter. So 0.1 would be 10% of the model diameter. So for an object of 2 meters, that would be 20 centimeters. And we're showing this as a function of the distance from the camera to the satellite. So going from 1.5 meter to 30 meters. And you'll see a fairly nice trend. So even at 30 meters, we're still quite accurate. We see that the error decreases as we're going closer and closer to camera, up to a point where we start being too close. And it's now we only see a partial view of the satellite because of even though we have a wide angle camera, it's not wide enough to really see the full satellite, and then we'll start losing it. This is not a real problem in a realistic application because there's a point where you're sufficiently close to the satellite such that the dynamic motion model that is used in the guidance and navigation and control elements is good enough to propagate the motion, and we don't really need to estimate it from images anymore. We just know what the motion will be in the very near future to actually do the grabbing of the Vespa. And so, well, these are some numerical results, but here are some visual results for the two data sets. So here's this sequence of the Swiss cube, which has this particularity of having this big antenna over here that we're seeing here. And this is some results for the Vespa, seeing some variations, some also part of the Vespa exiting the image in that case. Of course, we're not doing simulations that are realistic approaches of the Vespa. These are just sequences of the Vespa moving around roughly in front of the camera. Now, we were quite happy with this, but we we're also realizing that there were some challenges. So these were results on synthetic data. But of course, we need the method to work on real data. Now, we cannot simply, for space applications, have access to real images of the satellite, the Vespa in our case, in space. We actually don't have any images from space. We can see traces of it by using telescopes from the ground, but from space we don't have any real images of it, and it will be very expensive to acquire it. It means launching a mission to go to space, right? And then you'd have to download all of the sufficient amount of data, annotate it manually, and train a model, upload the weights of your network to space, and then eventually you can do the mission, which would be, expensive both time-wise and money-wise. And we thought, okay, maybe if the images are realistic enough, our network trained on synthetic images might generalize to the real ones. But despite what we were doing, we couldn't get this to work. We found in our training there's still differences. This is maybe a bit of an extreme case. We could maybe be closer to the real images, but even if we try to be as close as we could to the real images, training on synthetic does not generalize really well on real ones. So we had to find a way to learn to generalize, even ideally in the absence of any real images. So the way we treated this is by treating pose estimation as a refinement process. So what we realized is that if we do enough data augmentation on a synthetic data, then training on synthetic data gives us somewhat good results. They're not great results, not sufficient to actually do the mission, but they're not completely absurd, right? So you get, synthetic data like this, you do a lot of augmentation with noise, with color transformations, and all sorts of things. You train your network on this synthetic data with this data augmentation, and then, results on synthetic data are great. Results on real data, they're not great, but at least the object, if we're considering that this is a bigger picture, the object is roughly at the correct location. It's not in perfect pose, but it's not too far off, right? So what we thought of is, given this initial results, we'd like to refine this initial pose to improve it and so that it better matches the real images. Now the question is still, how do you do this without any real data, right? And so the standard approach of doing this would be to say, okay, I'll iteratively render my object and compare it to the input image, and then predict the delta pose. But that means to be able to train this kind of refinement method, you need real data as well. Because if you just train this kind of iterative refinement with synthetic data, it simply doesn't work, doesn't generalize. It suffers exactly from the same problem as the original network. What we realize, however, is that optical flow prediction generalizes much better across domains. So optical flow consists of predicting a displacement between two images. So what we did is train a network for optical flow estimation between what we refer to as exemplars, so synthetic but images that don't look realistic at all, right? Really very basic synthetic images, and more realistic synthetic images like this one. And so we saw that if we trained our optical flow network only on this type of data to predict a flow that's depicted here with column map, then it works well on this similar kind of synthetic data, but it also works well when you have an exemplar and a real input image. And so here is an example. This is the ground truth flow between this exemplar and this input image, and this is what we're predicting with a network that was only trained to predict optical flow with this kind of pairs of images. So that means that now we have an algorithm that goes as follows. So we first have a deep network that does an initial pose estimate. Given this initial pose estimate, so it takes this image as input, it estimates the pose of that particular object. Given the estimated pose, it's not perfect, but we can still crop the object of interest. So we get an image like this. In addition to this, given the initial image, we can render a rough exemplar. Nothing realistic, but still that's fine. And then given the exemplar and the initial image cropped, then we can estimate a dense 2D flow. Now, in the exemplar, we know where the 3D points are. We have now 3D points to 2D point correspondences with an additional flow. So now we have correspondences between the 3D points and the object in that small image, cropped image. So given these 3D to 2D correspondences that we get from the flow, we can estimate the delta pose and then obtain the final complete pose after the refinement. Now, the problem is that this still requires us to render an exemplar of the object in the initial pose at test time. So that means that for every image you do, you get an initial pose of your object, you render an image, and then you apply your flow network. So rendering at test time is quite expensive. So instead of doing this, we rendered prior to test time a set of exemplars. So essentially for any object, we have a number of an exemplar set showing the object in different poses. And then once we have the initial pose, we'll retrieve the closest exemplars based on the initial pose, so the ones that have the most similar pose. We'll retrieve potentially multiple of them. For each of them, we predict the optical flow, so we get multiple optical flow predictions. So that gives us more 3D to 2D correspondences that we put together in the PNP step to get the final pose estimate. And so that avoids us from having to render exemplars at test time. So here are some results, numerical results on standard computer vision benchmarks. So to give you an idea, the watercan that I was showing is from this line mod data set, and occluded line mod is a similar data set but with more occlusions. YCB is the kind of images that I've shown you the video of before, so also more household objects. So results for these three data sets, the ADD01D metric measures the percentage of objects for which the pose error is less than 0.1 times the diameter of the object. So the higher the better, so it's success rate really. And so we're comparing our approach to a number of baselines which all have been trained using real images of these data sets. By contrast, here ours plus 0 means that we've only trained our approach on synthetic data. So by only training on synthetic data, we're getting accuracies that are on par with the good performing ones of these methods. Maybe not the very top one, but still, good performing ones. Now, if we additionally use 20 annotated images per object to further train our method, then we can improve our results to do better than the best performing method that was trained on hundreds of images per object. So these are quantitative data. Now, what about going back to space and applying this strategy in space? So these are the results of this. So in that case, we trained a network on synthetic images, the kind of synthetic images that I've shown you before. This gives us the initialization. We then trained an optical flow network on synthetic images as well. And now we're applying these two networks on these real images. So these are real images not taken in space. These are real images taken in a lab environment with a robotic arm holding a mock-up model of the satellite and moving it around. But still we see that based on, by comparing the green contour with the red contour, we're seeing that we're getting accurate pose estimates. Now, until now, the results that I've shown you, they always assume that, and the methods to get them, we always assume that we have access, we know the object, and we've trained our model for the object. And this is similar in space. So the existing solutions, so ClearSpace 1 mission, the ELSA-D mission of astroscale, they always focus on one specific debris of interest. But of course, if we're looking at the picture that I showed you at the beginning, well, there are tens of thousands of debris. And some of these debris, as I said, are known because they are known non-operational satellites, but some other of these debris are simply unknown because they're actual debris resulting from a collision. And so we cannot possibly train models for all of these debris. So we need to be able to generalize to objects that we've never seen before. So we've started to take a few steps in this direction, and in particular trying to estimate the 3D orientation of unseen objects. Now, there are methods that work at the category level. So you have multiple instances of the same category. For example, cars. You train a model for cars. You see different brands of cars, different shapes of cars. And now you can apply your model to a new car that you've never seen before that might be different in shape. This is still reasonably easy in the sense that, all these cars, they look fairly similar to each other, so you can generalize reasonably well. Now, what we want to do instead is be able to generalize to categories that we've never seen before. So really, we have training objects that maybe look like this, and we train only on these objects, and we want to be able to estimate the pose of these test objects that look completely different. So how do we do this? We do this via a form of retrieval. So given a new object, and at this point, we're assuming that we know we have access to a 3D model of the object, of the new object. What we do is we render the object from different viewpoints. So we create a database of template images of these objects seen from different poses. And then we cast the problem of estimating the pose as a retrieval one. So given the input image, we're looking at this object, comparing it to every template, and based on a notion of similarity, we'll simply pick the closest object, the one that is the most similar, and assign the pose of that object to our input image. So we train a network to do this kind of comparison. So compare a real image to a template image, a synthetic template image, and this generalizes well to new objects. So it's much easier to generalize this notion of comparison of two images than to generalize a direct prediction from an input image. And in particular, what we're doing is we're looking, instead of looking at global representations of the object, which has been done in a few previous work, what we're doing here is trying to compare local features. So we have on one side the template, on another side the input image. We extract feature map, but now we're comparing local features among themselves, fusing all of these similarities, local similarities, into a global similarity score that we found to be more effective than the global methods. Furthermore, of course, that means that we need to compare the input image to all of the templates, which can be expensive. So we have a faster strategy of doing this. We first select a number of anchors in our templates, sparse anchors across the whole space of templates, shown in red over here. We find the most similar one among these anchors. So because we have a small number, this is fast. Once we've found the most similar one, then we take the nearest neighbors of these most similar ones, find the most similar one among this nearest neighbor, and then refine this process in stages, which allow us to be much faster. So here are some results, many numbers, but we don't need to look at all of them. But so these are simply different partitions of the data between known and unknown objects, seen and unseen objects. And we're comparing our approach in terms of recognition accuracy. So are we able to correctly recognize the object of interest if we have multiple objects? And the rotation accuracy, how well can we estimate the 3D orientation of the object? So we're only focusing on orientation at this stage. We don't try to detect the object to estimate the translation. Now, the point of these numbers is really to show that when it comes to the seen object, our method might not be the best performing one, right? So there are methods that are more accurate at estimating the orientation of seen objects, but for the object that we've never seen, we're much, much better. So there's a big gap here when it comes to unseen object, and a relatively small gap when it comes to seen object. So here are some examples of this, just a few to illustrate, the input image. Here are 3 images and the different methods. So some of them retrieve an incorrect object, some of them retrieve the correct object, but in an incorrect pose, and ours is better at estimating the correct object in the correct pose. So We haven't applied this for space yet because we don't have any data for this, right? So this is more about a step into the future. But of course, this is in practice going to be useful for space applications to generalize to unseen objects. Now, as I said before, one of the limitations that we have. So now we have a method that estimates that can generalize from synthetic data to real data, and that can generalize from seen object to previously unseen objects. Nevertheless, as I said before, we're only able to handle the rotation of the unseen objects. So we're assuming that we can detect these objects. So now we need to find a way of detecting previously unseen objects. So to have some model that can extract objectness or can propose objects so that we can then estimate the rotation for these objects. The other thing that we're assuming right now is that we have access to a 3D model even of the unseen objects so that we can generate our templates for the unseen objects. Of course, we'd like to be able to reconstruct objects that we've never seen before. Can we try to do this via structure from motion in a traditional way? Can we do a learning-based structure from motion that generalizes to objects that they've never been seen before? This is also future direction. And of course, in terms of other applications in space, there could be applications in asteroid landing, trying to estimate the pose of an asteroid so that we can approach it and land safely on it. And when we're looking at detecting previously unseen objects, we can imagine applications in the context of space monitoring. And so this concludes my talk. Thank you for your attention. I'm happy to answer some questions.
Perfect. Thank you very much. Very interesting talk. I think I will start with the first question and then everybody can join in. I was wondering, like, two things. One, you mentioned the notion of time, and I mean, this goes also a bit in this like structure from motion over time. Is there a reason why you didn't integrate it in the first place in the networks you showed before? And if you would think it's helpful, how would you integrate it? I mean, I guess you just have more information, especially if you think in the context of flying towards the object of choice, right? You would see it a lot. You would see how it turns. So would.
Yep. So there are two things there. The first one is that we need to be able to get a first estimate of the pose from an individual image without knowing anything a priori. Because there's really a point where you don't know anything about the object, so you need to estimate its pose from nothing, which and this is what we refer to as pose initialization. And then, in fact, in a mission, we go from initialization to tracking. Once you've got some reasonable initialization, you can start to track across the frames. Now, even for initialization, we've been looking at using dynamical model to try to make the initialization more robust, to be able to filter out the wrong initializations and things like this. So this is also something that we're looking into. And of course, in terms of tracking, one thing that we started looking into is simply using our refinement-based strategy for a tracking application. So you have an initial pose that is from one image. Now in the upcoming image, the pose is not too far, so you can simply refine your initial estimate and do this form of tracking over time.
Yeah. And just in the context of this, I mean, if I understand it correctly, you already know which object would be for the first mission, would be part
That's
of
correct,
your.
yes.
Yes. So I was wondering, like, you should, like, how would you choose it if there are multiple around? Is there also like some sort of like selection process, or is it very unlikely that there's something similar while you, like, let's say there are two objects that look quite similar and you.
No, so so in a space mission, this is virtually impossible for this to happen. In a sense that we know the orbit of the object. So there are many objects, but still distances in space are very large, right? So no, I think there's essentially no risk. Now the other thing is even if there were risk, I mean we're looking for one particular object, so the network is trained for that object, so it will in fact detect the object, right? So this idea of using a form of segmentation at the same time as we're predicting the pose would allow us to find the correct object, even if there was another one. If they look very similar, then of course that'd be difficult. But
but if you know what is happening, and so you would also fine tune it for that specific object that you are looking for.
Yes. I mean, there's no secret about the object itself. It is the Vespa, this conical kind of object. This is
Okay.
the object.
This is the object you're looking for.
This is a
Okay.
mock-up of the object, but it looks like this. Yes.
Okay, perfect. Yeah, I think that was it from my side. I mean, thanks again. If anybody else has some questions, feel free to ask them now.
Yeah, I found this really interesting. I don't know if you're familiar with the thousand brain theory from Jeff Hawkins from the Numenta company, because like a lot of the things that you mentioned really reminded me of that theory, and that theory is basically how our brain itself is sort of doing the post estimation on in itself. That this is basically the fun that theory sort of proposes, that is like one of the most fundamental sort of algorithms that the brain kind of implements. And a lot of these things also, especially basically from local information, trying to sort of define the relative coordinate system, so to speak, of the objects, that really reminded me of that theory. And I find it really interesting that that there are so many similarities. I don't know if you are familiar with
So no, and as a matter of fact, I did not understand the name of the theory that you said.
1,000 brains.
Okay. No, I'm so sorry. I'm absolutely not familiar with the theory, but that sounds very interesting. Yeah, I'll look into it because I think one thing that we're missing here, and sort of a general rule for deep learning really, is a better understanding of what's happening in the network, right? So now we have a network that's able to make good predictions because it's been trained on data, but we don't really understand why. And when it's making mistake, we don't really understand why either, right? So I think getting a better understanding and maybe getting inspiration from what's happening in the human brain, that could also be an interesting way forward to better understanding what's happening in deep networks.
Yeah, I think it really can also benefit potentially in both directions, because like sort of, so it's the company that's behind it is, or it's a research facility as well. It's called Numenta. And they basically doing like a different approach. They're doing a more top-down approach. So basically they think about basically what kind of algorithms could the brain implement, rather than reverse engineering basically how the brain structure looks like, because it's so complicated that theoretically could find any kind of algorithm there. And so they're doing it the other way around, which is in that field is quite unique, because we have a lot of data about the brain, but there is no, or like the fundamental theory, what it's actually doing is missing. And so they applied in that notion and called it a thousand brain theory, which is again sort of, and the thousand brains comes from that basically the brain doesn't have a single model for some object, but the object is modeled across a lot of many parts of the brain, which sort of does it in a local fashion, looking for individual features. And then there is sort of some kind of maybe global voting system or so, where all these individual models sort of vote on what is, for example, seen or so. And this really reminds you of the approach you're taking there as well. So it was quite fascinating.
Oh, thanks. Yeah, I'll definitely look into it. This is very interesting. Thank you.
Maybe a question more related to the hardware side of the mission. Given how the error rate is rising as the object is coming really close to the camera, do you plan to have any other specific type of sensor embedded on the hardware itself, or is it going to be camera based only?
So there will be other sensors, but not for the reason not for this reason. In fact, the other sensors are rather dedicated to finding the object when it's further away. As I try to mention during the talk, the thing that we saw, the behavior that we saw at less than 2 meters is not really a problem, because at that point we're so close that we're really going for the capture. There's of course a dynamical model that's going on in the background, and so that means that we're very close to the capture. There's very little time between the current time and the capture, and the dynamical model is able to propagate the pose information that it has accurately at that stage. So in fact, there's no need to go to 2 meters for pose estimation. When you reach that point, you can just let the dynamical model predict the pose, and then you just grab it in this way.
Okay, yeah, makes sense. And just and so maybe that question is linked then. What kind of latency can you have in such a network in terms of speed of approach and then the speed at which you can grab the object? Are we talking milliseconds because the approach speed are, or is it something where it's not so much of a constraint?
It is somewhat of a constraint, but it's not. We're not talking about milliseconds. We're talking about having something that runs at a few frames per second, but between 2 and 5 frames per second, let's say.
Okay, great.
And it also depends at what stage. So if we're talking about estimating the pose from an individual image when we're far away, then we can afford to spend more time on this. But as we're tracking and then we're coming closer, then of course we want to make sure that we have up-to-date information.
I had a question regarding, I mean, first of all, thank you for your talk. I really enjoyed it. What kind of next hurdle can you envision when it comes to applying actually it in space on the device? So you had things in space are far and they can also be close. Then you solve that. And then, synthetic images don't generalize too well. Then you solve that. What is the next hurdle that you imagine?
I mean, the next hurdle remains this generalization to previously unseen objects. As I said, we've done some steps in that. We can estimate the orientation, but we can still not detect completely arbitrary objects, although in space that might not be such a big issue because it's not a crowded place, so detecting something should be fine. But our approach is still requiring having a 3D model. So really what we need to be able to do is either have a way to get rid of the 3D model entirely for 6D pose estimation, but that's a bit unclear because if without a 3D model, it's not even clear how you define the pose, right? The pose has to be relative to something, or go along the lines of 3D reconstruction for previously unseen objects. And structure from motion is, of course, working reasonably well when you have large scenes with quite a bit of texture, quite a bit of feature points that you can match, but for some kind of debris, I doubt that it would do a good job. So I think this is really the next big hurdle.
Thank you.
But we're talking about years from now, right? So first, let's get a mission on one debris that we know, and then we'll see.
Just out of curiosity, when is this planned so far? Like, what is the timeline, the rough timeline looking like?
The mission is planned to launch in 2025.
Yeah, I think. Okay, no, sure.
Yeah, for the problem of handling new objects or unseen objects, especially in space, wouldn't it be sufficient to basically have like a collection of sort of some kind of shapes that could be seen, and like, do the objects really need to be identical to the seen object, or does it basically just need to be close enough, and then sort of having a collection of I don't know how many objects would be sufficient to cover basically all the cases?
That's an interesting point. So I've never thought of that. I think this is an interesting point. You could have a large enough collection of objects so that you get something that's similar. I don't know how practical that is, to be honest, because when we're talking about debris that result from actual collisions, their shape can be pretty much anything, right? And their sizes as well, right? So I've talked about 34,000 that are more than 10 centimeters in diameters, but 10 centimeters, it goes from 10 centimeters to several meters. And then, of course, there are all the debris that are smaller than 10 centimeters in diameters that are the results of collisions, for example. So I think it would be worth investigating, but I'm not sure how practical this approach would be.
I mean, I was thinking that especially at a distance, I guess the objects, like the sort of a lot of object forms collapse to like certain kind of shape. especially, for example, if you could make a model which sort of has some shape invariances in there. So basically, like it could be the length could be different, or so wouldn't really affect the estimation.
I mean, yes, going in that direction and pushing it even further, I would say one possibility is to have a capture system that's not sensitive to the orientation. If it's only sensitive to the position, then all you care about is really being able to put the 3D bounded box around the object, and you don't care about the way, the precise shape. I don't think that would fare very well with, for example, the ARM-based strategy, but maybe with some other capture strategies, that could be an option, yes.
Yeah, actually, to sort of also refer back to the theory I mentioned, it's sort of assumed that in the brain sort of doing the two things in two completely disjoint things, like basically estimating where the object is relative to basically yourself and how the object is actually oriented are sort of some completely, or actually what even the object is, are sort of two completely separate aspects, where there actually were some human studies where you sort of can block one of those, and sort of like with some magnetic fields, you can sort of disable certain areas, and then, for example, you can only tell where an object is, but you just know there is something, but you have no idea what it is. And if you do it in reverse, you basically know what it is, but you have no idea where it actually is.
Yeah. Yeah, I'm not too surprised by this. Interestingly, there has been some recent work, not by us, but there has been some recent work that does the prediction of the translation and the prediction of the orientation in completely separate streams. So yeah, I guess they're going in that direction well.
And maybe just to bounce back on the very first part of Fabian's question, for unseen objects, you do have, I guess, 3D models of the sub-PCs of each and every satellite out there, or have probably like a way to retrieve that? Or would that be a too bold assumption? And
in theory, you're right. In practice, I don't know how much people are willing to share this kind of information, but
yeah.
In theory, you're right. Yes. But collisions can literally destroy and break things in two, right? So in that case, you don't have the model for that.
Yeah, I was thinking of a generative approach, maybe to like taking those components and then maybe like generating a data set to assemble them, or to assemble parts of them, because I guess there's also physical constraints on stuff that can break and cannot break, or that are probably easier to break. As long as yeah, but I guess it would just make the problem become probably a lot more harder if you need to approach it in a supervised manner, and then consider that each element is a subset of something you've trained on, because there could be possibly millions of classes.
Yeah, I'm not sure how I would approach this, but again, this could be an interesting direction to look into. Yes.
Okay, I think if that's, does anybody have another question? Okay, perfect. Yeah, thank you very much again. Very, very interesting talk. Thanks for giving us an insight into how you want to do this, and thank you everybody for coming. And yeah, if you're interested in general, we will have this every month from now on, promised. And I will send an email around soon with the talk for next month. Okay, guys, thank you very much. Bye-bye.
Thank you. Bye.